Going on to the next section of your parametric graphing notes, let's talk about how to write parametric equations. So let's say we have an equation right here, 3x plus 4y equals 24, which is not in parametric form. How do we put that in parametric form? Hopefully you'll notice that with an x to the first and the y to the first, this is just the equation of a line written in standard form. Well, here's the idea in general. Get variables on opposite side of the equation. So notice right here, the first time I subtracted 4y from both sides of the equation. Set each side of the equation equal to t. Well, since they're equal to each other, I can set them both equal to t, and that's still a true statement. So 3x equals t, 24 minus 4y equals t. Then solve each of those for t. So x is t over 3, and y is negative t over 4 plus 6, dividing everything by negative 4. Now you might think, well, I could have done that a different way, and it's actually true, you could. Instead of subtracting 4y from both sides, I could have subtracted 3x from both sides and have 4y equals 24 minus 3x. And then I have 4y equals t, or 24 minus 3x equals t. Dividing this both sides by 4 here, I get y equals t over 4. And dividing everything by negative 3, I get x equals negative t over 3 plus 8. Now this third one I'm going to leave for a minute and come back to, but there's actually multiple ways to write a set of parametric equations for the same curve. So all of these would be considered correct answers. However, in some cases it's easier to do something else. When I have y equals 2 sine of x, notice I already have variables on both sides of, opposite sides of the equation. So I could say y equals t, or 2 sine of x equals t. However, if I solve for x in that case, I would have to use inverse sine, and I don't really like having to use that. I'd like to have a nicer, kind of a cleaner way to write it. Same thing over here. I could say y equals t, or x cubed minus 2x plus 3 equals t. And how in the world am I going to solve that for x? That's going to be really challenging, if not impossible. So there's another way. I can solve my equation for y and just let x equals t. So in this case, I would have x equals t as one of my equations. Well, if x equals t, then I can just substitute this in t in for x. So then y equals 2 sine of t, and there are my parametric equations. That works perfectly well. Here I would say x equals t. I'm writing with my finger, so sorry this is kind of messy. Y is equal to t cubed minus 2t plus 3. So these are perfectly good parametric equations, and so I'm going to go back and do that with the previous one. So if I had solved this one for y to start with, I would have ended up with y equals negative 3/4 x plus 6. Then I would let x equals t, and then y equals negative 3/4 t plus 6. Now if it had been easier, I could also do the same thing by setting let y equals t and then substitute t for y and write my x equation. It would just depend on how the original equation was written, which one would be the easiest to do. Now I want to go back and look at example 1. We see 3 different ways to write parametric equations for the same linear equation here, and I want to show you what this looks like when you graph all of them on the calculator. So I've graphed all 3 of them, not necessarily in the order that I did them in, and I want to highlight. If I go over here, notice there's the red. That's t over 3 and negative t over 4 plus 6. If I do this black part, that's the t over negative 3 plus 8 and t over 4. And if I do the blue part, that's the last one I did, where x equals t and y equals negative 3/4 t plus 6. Notice they're all the same line. It's just that by using different equations, I get different sections of the same line, because if I were to click on any of these, you'll notice they're all going from 0 to 6.28. If I go up to the t1, 0 to 6.28. If I go down to t3, or to the third equation, 0 to 6.28. Now if I were to expand the number of values for t, or if I put negative values in, we'd get exactly the same line for all of them. But when we have a limited amount of values for t, notice that we're getting different sections of the line for each equation, but it is all the same line. Okay, let's go on to the next section, which is on the next page. I just want to do this little top section and then we'll leave the rest for the next video. Using parametric functions to explore inverses. It says different example on video. That's an old video, so it's obviously not a different example on this video, so we can ignore that. I have graphed a parabola here in parametric form. X equals t, y equals 2t squared minus 3. Notice, since x equals t, I could just call this y equals 2x squared minus 3 in regular form, in rectangular form. Now let's see what happens when we switch the equations. Instead of x equals t and y equals 2t squared minus 3, I'm going to do it the other way around. X equals 2t squared minus 3 and y equals t. Note, I use negative 10 to 10 to get the whole graph. I think I can actually use negative 6.28 to 6.28 and get the whole graph anyway. So let's go to my calculator and to the next slide here. Okay, so there's the original one. So now I'm going to go to tab and put it in the other way around. So 2t squared minus 3 and then t. So let's see what it looks like. Well, I only got half of it. I forgot to change my t step. So we'll just put in negative 10 to be fast here about that. Okay, so I got the bottom half now. Notice that these graphs have a special relationship, and you can see if I put in one more line, if I put in, actually I want to do this other one in just rectangular form. Let me escape out of here, and we'll add in another graph entry edit function. I just want y equals x. It's interesting, on your calculator you can do them all in different ways. Remember that inverse functions reflect over the line y equals x, so these are inverses of each other. And notice the second one I graphed is not a function, so it allows me to graph the entire inverse even when it's not a function. So switching the t and the x of t and the y of t functions just gives us the inverse. So this is a really easy, nice way to graph inverse relations even when the inverse is not a function. Okay, so you might want to just write that down. I'm going to type it in because that would be easier to do neatly. You get the graph of the inverse. And I'm going to put which is not a function in x comma y form, rectangular form. Okay, so that's the end of the notes for right now.